Welcome to Paper Simplified, a podcast brought to you by SILMA AI. Today we're going deep on a paper, it's called SuperBPE, Space Travel for Language Models.
Yeah.
Pretty interesting title. And the authors are Elisa Liu, Jonathan Hayes, Valentin Hoffman,
Mm.
So Wong, Noah A. Smith, and Yejin Choi. So quite a few.
Mhm.
You shared this one with me because you were really interested in kind of how language models are processing text.
Mm.
And also, what are some of the more recent kind of breakthroughs that are making them more efficient and better? And we're going to try and keep this approachable,
Right.
not too much technical jargon.
For sure. So kind of the high level points and, takeaway.
Exactly, exactly. So the main idea here is that they're presenting a new way to break down text for language models, and this is moving kind of beyond the traditional way of doing this with subword tokenization. And they're
Uh-huh.
bringing in these superword tokens. This is almost like teaching the language model to recognize
Mm.
common phrases as a single unit. So instead of breaking down, by the way, into individual words, it would look at the whole thing, or, search engine, things like that.
Yep. Yeah. It's kind of learning to group those meaningful chunks of words together.
Right, right. And the authors make a pretty interesting point that, the standard approach of just using subword tokens and being kind of limited by white space might actually be holding back what language models can really do.
That's right. I mean, if you think about it, white space isn't always a perfect boundary for meaning. Like in English, we've got these multi-word
Oh,
expressions,
yeah.
right, that function as a single concept, like
What are some examples?
on account of, or piece of cake.
Oh, yeah, we get that as a whole.
We understand it as a whole, yeah.
Right.
Hmm.
So that's one issue. And then also, if you think about how concepts are expressed across languages, something that might be a single compounded word in one language might be several words separated by spaces in another.
So the example they give in the paper is, spacesuit helmet in English versus Romanzukelm in German.
Wow.
So if we're just relying on these English white space boundaries,
Right.
it might make it harder for models to actually grasp those natural groupings across languages.
And even more so if you think about languages like Chinese and Japanese, where they don't even use spaces.
Right.
So their tokenizers are already kind of dealing with units that span multiple words,
Exactly.
in terms of like what we would consider words in English.
Yeah.
So how do they address this, right? Like, okay, if they're making this argument, what's the solution?
Yeah. So they introduce this thing called SuperBPE,
SuperBPE.
which is a modification to this really commonly used algorithm called byte pair encoding.
So that's BPE.
BPE, yeah.
Okay, and that's kind of like the standard approach for this, right?
Yeah, it's pretty much the go-to for tokenization these days.
Okay.
So SuperBPE basically builds on that.
Mm.
And the way it works is it incorporates this two-stage pre-tokenization curriculum, they call it.
Okay.
So in the first stage, it actually works just like regular BPE. It learns these subwords, within white space boundaries. But then in the second stage, it stops using white space as a hard boundary. And it allows itself to learn these superwords, as they call them, that can actually bridge across those spaces.
So like machine learning could become a single token,
Exactly.
even though there's a space there.
Exactly.
Yeah, okay. Okay, that makes sense. So, I mean, what are some of the potential benefits of doing this? Like, why go through all this trouble?
Yeah, so there are a few big ones. So first of all, more efficient encoding of the text.
Okay.
So you basically need fewer tokens to represent the same amount of information.
So that means faster processing, right?
Exactly, yeah. Fewer tokens generally means less compute,
Uh-huh.
both for training these huge models and for actually using them, in the real world, which is called inference.
Right.
And then potentially also a better understanding of meaning,
Okay.
because you're grouping these semantically related words together as a single unit.
Right, like search engine, like we were saying.
Exactly.
It's
Yeah.
like one idea.
Exactly.
Okay. So how did they actually test this out? Like, how did they see if this actually works?
Yeah, so they did a bunch of experiments where they pre-trained these large transformer language models.
Okay.
And these are pretty big, like 8 billion parameters.
Oh, wow.
Yeah. Um, and they were really careful to control other factors like the model size, the vocabulary size, and the amount of compute used for training. So the only difference between the models they were comparing was whether they used standard BPE or their new super BPE method to create the vocabulary.
Oh, I see. So they're really isolating
Exactly.
the impact of that.
Yeah, just to make sure it's really the tokenization that's making the difference.
Okay. Okay, cool. So what did they find? What were the big results?
Well, the results were actually pretty impressive. So on average, the models trained with SuperBPE showed a 4% absolute improvement for 30 different downstream tasks.
Wow.
Yeah. And to give you an idea of how significant that is, like usually to get that kind of improvement, you need to make pretty big changes to the model architecture
Right.
or use a lot more training data.
Right. Way more data.
So the fact that they got this just from changing the tokenization is pretty remarkable.
Yeah.
And then even more impressively, on this one benchmark called MMLU,
MMLU.
which tests a really wide range of knowledge and reasoning abilities,
Mm.
the improvement was even bigger, like over 8%.
Okay, so that's huge. And
Okay.
it wasn't just about being better, right? Like it had some efficiency benefits too, didn't it?
Yeah, exactly. So besides the performance gains, they also saw that super BPE models needed significantly less compute during inference.
Okay, so that's when the model is actually being used.
Yeah, exactly. So they needed about 27% less compute. So it's both more accurate and more efficient, which is really what you want for real-world applications.
Yeah, it's a win-win.
Exactly.
Okay, so they must have looked into like why super BPE is so effective, right? Like what's
Yeah.
going on under the hood.
Yeah. Yeah, they did some analysis, and it seems like super BPE leads to this more uniform level of difficulty for the model to predict each token.
Okay.
So with standard BPE, you often have these really common individual words that are super easy to predict,
Right.
like the or a or is,
Right.
and those lead to very low prediction loss.
Okay.
But with super BPE, because you're creating these tokens for common multi-word expressions, you're kind of grouping those easy words into larger units,
Oh, I see.
right? So like a phrase like, on the other hand, comes a single token.
Right.
So the model doesn't get as many of those easy wins on individual words.
Okay.
But at the same time, they also found that Super BPE had fewer instances of really high prediction loss,
Okay.
meaning the model was more consistently good at predicting even the difficult tokens.
So it's not like it's excelling at the easy stuff and then bombing the hard stuff.
Yeah,
It's more consistent across the board.
exactly.
Okay. And I remember reading something in the paper about like the computational cost of actually training the tokenizer itself.
Oh, yeah, that's an important point. So they did note that training the Super BPE tokenizer, especially when it's merging across white space, does require a bit more memory and CPU time compared to standard BPE.
Okay.
And that's because it has to consider a lot more potential merges initially.
Right, right,
But this is just a one-time cost during the vocabulary creation phase.
right. So once you've built the vocabulary, you're good.
Exactly, yeah.
Yeah.
And it's pretty small compared to the huge amount of resources you need to actually pre-train the language model itself.
Right. It's dwarfed by that.
Exactly.
Okay. What about the encoding efficiency? So like how compactly the text is represented by the tokens.
Yeah, so they looked at that too, and Super BPE was significantly better than standard BPE in terms of bytes per token. And this difference actually got bigger as the vocabulary size increased.
Okay. So why is that?
Well, it seems like standard BPE kind of hits a ceiling in terms of how efficiently it can encode text,
Okay.
because at some point it runs out of useful white space separated words to add to the vocabulary.
Right, right.
So it starts incorporating these less meaningful subword combinations.
Okay.
But Super BPE, because it can incorporate common word sequences as single tokens, it can keep improving its encoding efficiency even with larger vocabularies.
Oh, I see.
Yeah.
Okay, so it doesn't plateau as quickly.
Exactly. Yeah.
Okay. Now, I also remember them talking about these transition points in the Super BPE curriculum.
Right.
Like, when does it switch from learning just subwords to learning super words?
Yeah, so they experimented with that a bit, and they found that while the most encoding efficient transition point wasn't necessarily the absolute best for overall language model performance, all the reasonable transition points they tried still resulted in improvements over standard BPE.
Okay, so the basic idea is pretty robust.
Exactly, yeah.
Okay, and what about like the actual language modeling performance itself, like the bits per byte kind of metrics?
Yeah, so interestingly, when they looked at bits per byte directly, the Super BPE model actually had slightly higher normalized loss than the BPE baseline.
Oh, interesting.
Yeah. But as we were talking about earlier with the distribution of per token losses,
Right.
that doesn't necessarily mean it's worse.
Right, because it's more consistent.
Exactly. And it's still
Yeah.
showing those big improvements on the downstream tasks.
Right.
So it kind of highlights the importance of evaluating these models on a range of tasks that actually reflect how they're going to be used in the real world,
Right, right.
rather than just relying on these intrinsic metrics like perplexity or bits per byte.
Yeah, because those don't always tell the whole story.
Exactly.
Okay. Now, did they also look at like scaling this down to smaller model sizes?
They did, yeah. So they did some experiments with models that had like 680 million and 1.9 billion
Yeah.
parameters. And even in those smaller scale settings, the super BPE models generally did better, especially when they matched the inference compute of the BPE baselines.
Okay.
So it seems like the benefits of super BPE aren't just limited to these massive models.
Right, right. And I know they also talked about some related work in the field, right? Like, how does this fit into the bigger picture?
Yeah, yeah. They discuss other research on things like, alternative tokenization methods, multi-token prediction, and even tokenizer-free language modeling.
Okay.
But they kind of positioned Super BPE as this really simple yet effective modification to existing tokenization practices
Okay.
that offers these big advantages without needing to make major changes to the model architectures or training processes.
Right.
So it's kind of like a low-hanging fruit in a way.
Yeah, yeah. And I also remember them talking about some of the practical details of the tokenizer design.
Oh, yeah. So to prevent the creation of these super long, potentially meaningless tokens,
Right.
they put a limit of 4 words per superword. Yeah. And they also made this specific pre-tokenization step for digits, grouping them from right to left in blocks of 3.
Okay.
And that was based on some recent findings that this can improve performance on math tasks.
Yeah. Interesting.
Yeah. And then they also special cased the colon character to make sure it works well with common question answering formats.
Oh, okay.
Yeah.
So it's really well engineered.
Exactly. It's a very thoughtful approach.
Yeah, a lot of attention to detail.
Yeah.
Okay, so we've covered a lot of ground here on Super BPE. To kind of wrap things up, what are like the key takeaways and novel aspects of this research?
Okay, so I'd say the core innovation is this two-stage pre-tokenization curriculum for BPE, right?
Mm.
That allows the model to learn these superword tokens that can span across spaces.
Mm-hmm.
Um, and that seemingly simple modification actually leads to pretty big improvements in encoding efficiency, and crucially, also significant gains in performance on a bunch of different language tasks.
Right.
And it also comes with a reduction in inference compute, which is great. And the really novel thing here is that it's just this elegant extension of this widely used algorithm,
Right.
BPE. And it really shows the potential of moving beyond, just strict subword tokenization that's tied to white space.
Yeah, yeah.
And then the researchers also do this really detailed analysis of, the difficulty of predicting each token.
Right.
And that provides some really valuable insights into why Super PPE is so effective.
Hmm.
It suggests that it leads to this more balanced learning process for the language model.
Right.
And then finally, I'd say their attention to all these practical implementation details,
Mm-hmm.
like, limiting the superword length and special casing the colon character.
Mm-hmm.
All that really underscores the real-world applicability and robustness of this approach.
Awesome. Well, this has been a really great deep dive into Super BPE. I feel like I have a much better understanding now of how it works and why it's so impactful.
Yeah, it's a really interesting paper.
So thanks for joining me today, and thanks to all of you for listening. We hope this has given you a clearer picture of this exciting development in the field of language models. And as always, we encourage you to explore further, read the full paper, and let us know what you think.
Absolutely.
Thanks again.
Yeah, thanks for having me.